Safa Jamali here from Northeastern University in Boston. Thank you, Mike, for the invitation. It's my first time in Cambridge, hopefully not the last time. We'll see how it goes. So this is what I would say snippets of a little bit of a different explorations we have done in using different machine learning methodologies for rheological problems. So I won't be getting too much into details of each and every one, but I'd be happy to discuss any of those. The goal is to give you an idea of what we're doing in this general area, and this should motivate how crazy we are being with this topic. The whole idea we have is to build this Rheoinformatics made-up name as data-driven platform to unify experiments, theory, and computation all through the power of data-driven models. So maybe build something like a digital rheometer where data, theoretical understanding, simulation can all go together and teach us better rheology. So that's the general goal. See if we can get there. So again, just motivating this. My view of classical approach to rheology is you always start from maybe an observations. This one is simply just showing something like a thixotropic fluid or an elastoviscoplastic fluid, or maybe you have a goal of printing a complex fluid into structures. So generally what you do is you start from experiments. You basically pick a piece of material, put it on the rheometer, start testing it. You get a stress, strain curves, or similar representations of the behavior you're interested in. Then you go to theory and build some understanding phenomenologically of why that behavior emerges. This particular model we're going to come back to. This is isokinematic hardening for elastoviscoplastic fluids. And then if everything checks out in your model, then you basically can put that into a numerical solver and model it for different geometries and hopefully get something that you were interested in from the get-go. One issue here is that these are a little bit disconnected. And the secret motivation I've always had was if you have a considered model, doesn't matter how you solve it numerically, the answer is always the same. If you can make experiments, if you can do experiments and your predictions or model gets better every time, well, that's interesting. Can we do that? Okay, so basically build considered models that are informed continuously by experimentation. Okay, so how we got started in this whole area was, again, so this is the motivation, but before that, we're not the only group doing this. There are a lot of people that have been worked for the past few years and using different machine learning technologies in rheology. The general classification in my head is usually people have used it for flow modeling, and this was the work that Mike, for example, presented just now. Or you can basically look at this, again, listed in Mike's paper. Automated data handling and high throughput experimentation can do material modeling, characterization, or model discovery. This one I'm going to come back to a little later. We've done a little bit of a perspective article on this. This is, I call it a semi-recent review because every time you look at this, there are new works out there. So the pace is crazy fast. We can't keep up. But if you're interested in looking at a general view of what we have been inspired by, please take a look at that. The way we got started in this was in a collaboration with George Karniadakis at Brown University. PINS, you might have heard of it, physics-informed neural networks. The methodology is pretty simple. This sort of revolutionized the way we thought, the way we think about machine learning using automatic differentiation. The idea is you have input parameters and output parameters into a neural network. Automatic differentiation here allows you to get differentials of any output parameters with respect to inputs. And because of that, you can favor a certain solution. You can put in any differential set of equations, ODs or PDs, into softly or hardly into your neural network and basically make your neural network a counterpart to a MATLAB code. So you can solve ODs and PDs with it. So that's how we started. And these are, again, old data that doesn't look really too good, but this was how we started. This is what we call RINs, Rheology for neural networks. On the left is the numerical solutions, the ground truth. On the right is the RINs or PIN solutions for stress growth and Poiseuille flow of a Maxwell fluid. The errors are within 1 or 2% at most. Things are looking good. So we can build pins that are counterparts to your MATLAB code. Not really impressive. There are pros and cons to it. There are issues with pins being a little fragile here and there, but let's not get into it. This is very well studied, so I'm not going to get into details of that. But we're going to use this later on. This is how I would, this is what I refer to as explicitly imposing physical intuition into machine learning. But you can also do this implicitly through data. And the way we have done this is through multi-fidelity modeling. So bear with me for a second. These are dummy data. They don't mean much, but they're supposed to motivate why we're doing this. So imagine that these red guys are your high fidelity measurements of anything you're interested in. You only have a few of those. Maybe those are experiments you believe in, or maybe high resolution simulations you believe in. But those are the high fidelity data that you have. Then the blue guys here, more abundant, but not accurate. Maybe again, bad experiments or lower resolution simulation. Whatever defines as low versus high fidelity in your own perspective. This approach of multi-fidelity modeling allows you to basically learn the trends of low fidelity. For example, here, both are periodic. The low fidelity has the wrong frequency and wrong amplitude, right? But when you mix the two, you can make predictions at these basically pink or red dashed lines at the level of high fidelity without really having too many high fidelity data points. So that's really powerful. So we started with this in 2021. I'm not going to show you that, but maybe the more recent version of it in a collaboration with Norm Wagner and my former student Milad Saadeh did this work. The idea was, okay, can we, using multi-fidelity modeling and experimental rheology, can we predict linear and nonlinear rheological properties of a complex fluid? For the type of fluid, we picked Johnson & Johnson's baby shampoo. That was Norm's choice. The idea was this should be available to anybody who wants to reproduce the data, and the algorithms are open for anybody who wants to use it too. The general idea is basically high fidelity is the experimental data that Norm gives me. I'm going to explain now what the low fidelity is. In our low fidelity data, what we're doing is this. So my high fidelity data, again, is you'll see this in a better representation, more familiar representation in a second. But we are looking at steady shear viscosity at this point, 4 different temperatures at different shear rates. This is a pretty simple material. It's a Curry-Yasuda type of behavior. So you have a plateau at low shear regime and a shear thinning regime at a certain threshold. We do have a few different temperatures and a few different shear rates, the data for, but the way we get the low fidelity data is this. We said, okay, let's assume we know nothing about the material. So what I'm going to do is I'm just going to do curve fitting. I'm just going to basically a simple regression on the high fidelity model and get something like this. So my low fidelity map looks like this. This is a simple power law, right? It's off, but the general idea is that the viscosity is going down as the shear rate goes up. And with the temperature, it has the right trends. The difference is these are only a few, but you can, because this is a simple regression model, you can generate synthetically as many data points as you want. If you mix the two, the resolution you get is something like this. So you can now ask at any given shear rate or temperature, what is the viscosity? Okay. So far seems simple, but let me show you the actual data. These are, all the scattered points are experimental data. If they're filled, that means they were used during the training. If they're open, that means I'm just comparing them. They were masked during the training. And all the solid lines of different colors are the predictions of this multi-fidelity approach. So this is what I would call in-range predictions. So 10 degrees C all the way to 50 degrees C. And we are asking what is the viscosity at different shear rates for 20, 25, and I believe 40 degrees C. That works well. Okay, not really big of a deal. But what's interesting is it's also working for out of range. So not having seen the 10 degrees C or 50 degrees C, just mixing the two levels of fidelity, you can actually make good predictions of what the viscosity would be. And again, remember, we have no physical intuition about the system injected into the model. Okay, it's just coming from the curve fitting of the data itself. Now, again, this is simpler data, but you can now extend it to nonlinear behavior and basically transient data. This is stress growth, stress as a function of time, so that you can just see it easier. At different shear rates applied, the same thing. Field symbols were used during the training, open symbols were not. And you're seeing in range, so interpolation still works the same way. We are still doing the same thing. The low fidelity is only generated from simple regression of the actual data. And out of range for the highest shear rates or the lowest shear rate still works. Okay, so with no physical intuition, by just using basically synthetically generating low fidelity data from the actual measurements, you can make good predictions. Okay, so that's what I would call implicit intuition of physics. The reason I would call it implicit is whatever your low fidelity data is, it has some essence of the physical behavior you're trying to predict. Now, you're not explicitly putting it into the model, but it's there. If you generate enough volume of data, you hope to recover the physical behavior you want to observe at the end. So the next step is what we did by mixing the two. The idea is that the implicit and explicit physics intuitions are not exclusive, so you should be able to mix and match. So the idea was, if I have a descriptive consider model that I can solve with my neural network in any way, or MATLAB code, name it, and if I do measurements, add more and more high fidelity data, I should be able to use this as my low fidelity, and this is high fidelity, and at some point build a hybrid multi-fidelity approach where your considered model, again, is getting better and better every time you're adding high fidelity data to it. So let's see how it works. So this is where we collaborated with Simon Rogers at a UIUC and his former student, Rheoinformatics Kamani. I asked Simon for some rheological data that are not simple to model. So he sent me these data. I think they're complex, but these are fumed silica gels at intermediate volume fractions. You're looking at a stress growth test, for example, for two different applied shear rates at different waiting times. This is a thixotropic fluid, so it takes time as you see. Sorry about that. As you see these waiting times, as you give it more and more time, the microstructure builds up. So the response of the material is changing based on that waiting time. And these are the Lissajous curves from Laos to south, south to Laos, from small to large amplitude oscillatory shear. What we started with was the model that we wanted to pick as the descriptive model of choice. So this is what I promised I would go back to. This is isokinematic hardening model written by the group of Garrett McKinley for thixotropic elastoviscoplastic fluids. The general idea here is that you have a viscoelastic element, and then you have a plastic component here that has the idea of back stress or Boeschinger effect and kinematic hardening built into it. So you have to solve three coupled ODEs, one for time evolution of the microstructure, one for the back stress, and one for your viscoelastic element, together to get the stress, okay, at any given condition. So that's my descriptive model. That's, I might be biased, but I like IKH, so that's why I picked it. And we started with only 3 sets of data. So we had 3 different shear rates and 3 different waiting times. So I asked Simon to only give me that. So everything else that you're seeing, we saw it afterwards. So we're comparing it afterwards. From those three, we're recovering the parameters of IKH, and now we're just solving IKH given those parameters using our neural network for this particular case. You basically give it any waiting time you want, your microstructure parameter changes, your initial condition changes, your response changes. So these dashed lines are the IKH predictions. So the best model fit that you can get from limited number of experimentations. And the solid lines are the experiments for two different shear rates. We're doing okay with the elastic initial response and maybe the plastic flow at the end, but everything in the middle in the transient is off. You can, because this is now basically just a MATLAB code, you can solve for any given condition, right? So you can do it, you can do the solutions. These are steady state solutions for different frequencies and different amplitudes. The red lines that you're seeing are the IKH solutions for this particular gel, and the black is the actual experiments that we had not seen. At this point, we said, okay, we are making a lot of measurements or predictions. These are just model predictions of these different types of flow protocols. I asked Simon to send me 3 more of these black guys. That's it. So we started with 3 stress growth, and then we asked for 3 more sets of data picked out of these black guys. And when you mix the two and use the multi-fidelity approach, you get something like this green. So now your predictions are exactly matching the experiments. So that's why I say, now you add any more data, any experimental measurement, you're making this even more accurate. And at that point, I call it digital rheometry, because now you've learned enough about that flow protocol and that material that you don't have to do the actual rheometry anymore. You can just make predictions. Okay, so you can actually, let me see if this runs. You can actually use your neural network to tell you what model is correct. So I just told you that I have a bias towards this IKH, but the reality is you can build a library of different considered models and ask your neural network to tell you which one is the right fit. Basically put the data in the driver's seat and tell you what model has to be picked as the descriptive one. And this can be completely done without any user interference. So my view of digital rheometry to this point is you start from a limited number of experiments. You can actually use automatic model detection. Once you pick that model and its parameters, now you can, using the same neural network, you can make you can make predictions for any given flow protocol. Then you can construct this multi-fidelity scheme and add a little bit of additional experiments. And at that point, you can drop the rheometer and just make measurements. So that's our view of how we think about this digital rheometry concept. Okay, so all of these are basically assuming that there is a model, right? The other question that I always got asked whenever at the beginning of machine learning and rheology, I gave talks, question was, can data-driven techniques teach us new physics? Yes, many of you know SINDY. There was a discussion on SINDY. That's one way you can think of ways to learn physical intuition from observation, right? So this is a SINDY type, not exactly SINDY, but SINDY, by the way, stands for sparse identification of nonlinear dynamics. And the idea is that you have sparse observations of some behavior, and you build a library of different functions. You build a dictionary of different candidate functions, and use it using, again, automatic differentiation, for example. You can pick out which eigenmodes describe that behavior and then find the coefficients for it. So basically, from observations, it spits out an equation that describes that set of behavior, that set of observations. So that's what we did next. Again, collaborating with Simon, this is data from South to Laos on carbopol, viscoplastic fluid. And this is the type of behavior you get. And so basically no assumptions are made, only a library of all these different combinations of a stress, its derivatives, first, second derivatives of stress, deformation, their products, all sorts of crazy candidate functions, as long as they're dimensionally right. And then you ask Cindy to construct a model that describes this behavior. So what we found was this. So you have a stress, the time evolution of a stress as a function of basically 6 different groups. The coefficients don't matter, so you can rewrite it as this. Again, the coefficients don't really matter, but what's interesting is you have products such as gamma dot times gamma double dot, which is not exactly what you would see in a viscoplastic constitutive equation. So when I say teaching us new physics, maybe that's something we should pay a little more attention to. And by the way, if you get rid of this component, your predictions are going to be off. Now, how are we doing with that model? This is the model that I had just showed here. This is the model. This is the experiment. And this is Simon's model that was published 4 years ago in PRL based on recoverable and unrecoverable stresses. So the model is actually doing really good. We tried it on creep on different flow protocols. It's consistently predicting the right behavior. It ended up being thermodynamically consistent, which was not posed, but ended up being the case. So we were lucky in that, but that's something you may want to be careful with it as well. Okay, so far, everything I've shown you is basically data to data mapping, right? So you're going from X to f of X, and whether you're using a neural network or anything else, what you're doing when you go from X to f of X is you're approximating functions, right? But now you can also use neural networks to go from function to function. For example, if I go from one of these points to another point here, I've gone from X to f of X. If I go from this entire space to this space, I've gone from one function to another. So now I'm approximating operators. So this is another whole field within machine learning and scientific machine learning. And these are called neural operators that approximate operators that go from input mapping to output mapping. 2 big classes of those are depot nets, deep operator networks, or Fourier neural operators. They're very similar in details. One only works in Fourier space, the other one doesn't, uses 2 different neural networks. Details of that is really not that different and not that important, but I want to showcase what it does and how powerful it is. So we used both of those. The way you train these models, and again, you're going from input space to output space, right? So we're working on 2 different fluids, TEVP, thixotropic elastoviscoplastic. You have a time evolution for this microstructure parameter that couples with your constitutive equation for a stress and a strain. And we have a 2D Giesecke's fluid. We wanted to look at a tensorial representation as well. And the way you train these neural operators is this. You basically use something like a Gaussian random field, and you generate random representations of your input map. And because you do have the solutions, you can generate the solutions, right? So that's your input, that's your output. Any of these lines that you see, for example, for the Giesecke's fluid, different components of the deformation tensor are your input maps, and your output map is different stresses. Now, all of these are completely meaningless, right? The only thing you know is the right one is calculated from the left one put into this equation. So it's scientifically correct. It might be completely meaningless. And the idea is when you generate tons of Gaussian random fields, you've seen enough observations of mapping from input to output that now you can ask any given protocol and see how the model does, right? So let's see how we do with this. So operator learning for TVP fluid first, you're going to see a lot of lines, the exact line. The PI means physics informed depot net, physics informed FNO, Fourier neural operators, and the depot net and FNO. And all the lines are on top of one another. So basically now I'm applying or I'm asking questions about your conventional viscometric flows. So this is steady shear, step down shear, oscillatory shear, and one arbitrary flow. On the bottom, you're looking at shear stress. On top, you're looking at lambda or microstructure parameter over time. For all of those, you consistently predict the right behavior. And again, the idea is that you've seen enough mapping previously that you don't really need to explicitly see a given flow protocol. You've learned every physics there is. With the Giesecke's fluid, with pure extension, pure shear, simple shear, and again, arbitrary flow, on top, you're looking at the first normal stress difference. On bottom, you're looking at shear stress. Again, the same thing. You're consistently making good predictions. So these neural operators, when trained on enough set of data, are really, really powerful in predicting the behavior for unobserved protocols. Okay. So now where are we going with this? This was published earlier this year in Journal of Rheology. Now onto some unpublished data that I'm really excited about. This is what I call moving towards RheoGPT. So bear with me for a second. So transformers, you probably have heard of them. It's the T in GPT, right? So the idea is used in natural language processing and pretty much in all large language models. The idea is really, the core idea is replacing the recurrence with attention. And the attention is basically, when you look at a query, when you look at a large set of data, you want for each input to learn what to attend in other variables. Okay. Now, in language models, it's common sense, right? So you want to know each word is attending to another word in a certain location in that query. But you can do this exact same thing with scientific data. So my collaborator, Amir Barati in Carnegie Mellon, has developed this tool that he calls O-former, basically using transformers to approximate solutions of ODs and PDs. They've tried it for Newtonian fluid dynamic. Now we are making the Rheoformer with my student Maeda for different viscoelastic fluids. For example, this is Giesecke's fluid. The training is exactly the same way as I showed for neural operators. So you're making these Gaussian random fields. Again, the model and the attention idea, the transformer is learning where it should attend to, right, in this time series, or depending on your input-output functions with respect to different components of input and output parameters. So just to show you some results, these are normal stress differences, shear stresses for a Giesecke's fluid. You might say, okay, this is fine, but we just did that with neural operators, so not a biggie, right? But this is what I'm excited about. So these are actually full solutions. On top, this is open foam solution. On bottom, these are transformer predictions of an Oldroyd B fluid, where basically the training was done on one Weisenberg number, and what you're seeing here was not observed during the training. So what you can do is you can build these solutions, scientific solutions, of any complex fluid in any given geometry, and you can learn using these transformers and predict the behavior scientifically correct for a different unobserved Weisenberg number. So what that means is it's a long road, right? But if this works and if we can generalize this, then basically you can use the same ChatGPT, fine-tune it and train it on scientific data and ask the model to actually do scientific simulations of complex fluids. Using the same thing, so this is basically the velocity magnitude. These are shear stress, sigma xx and sigma yy. I'm showing these in logarithmic scale because the stresses are really small. So please note the range of changes that you're seeing in the color bars. But in all of those, the top half is the ground truth and the bottom is the prediction of what we call Rheoformer. So these are transformer solutions of an Oldroyd B, and you can predict any of the components of a stress or velocity in any given geometry. You can make it more fun, flow past the triangular obstacle at different Weisenberg numbers. This is velocity in the x direction, velocity in the y direction. So on the left, you're seeing the finally resolved numerical solutions. On the right is the transformer solution. and it's pretty stable for different Weisenberg numbers. I'll show you that in a second. But this is basically the stresses. Again, this may show you a little more deviation between the prediction and the ground truth. But if you look at the stress scaling, it's basically 8 orders of magnitude. The scaling is off. Anyways, so it's about 5 orders of magnitude. And because we're coloring this in a logarithmic scale, you're seeing, yes, this big of a difference. But again, these are pretty stable at different Weisenberg numbers. This is a Weisenberg of 0.2, 0.35, 0.9, and up to about Weisenberg of 5. That's what our simulation was really good for. Anything above that, the simulation actually broke down. So we didn't have data. So the goal here is, imagine with large language models, with GPTs. You train it on more and more and more data, you get better and better in speaking, in recognition of patterns, right? This is the same thing. We are just modeling the same phenomenon for the same sort of geometries. Now imagine if you add different types of fluids, different types of geometries, and build this library of transformers that are trained by a whole lot of different scientifically done complex fluid simulations. Now you can basically ask to run, and these predictions are pretty fast, right? Once you train it, the training is expensive, but once you've done it, the predictions are really fast. So you can actually democratize simulations of non-Newtonian fluids for a wide range of different conditions. Now, you may always need to start with simulations, numerical simulations, to fine-tune and provide training data to make sure you're predicting something correctly. But once done, these are extremely efficient and they're actually reliable. Okay, so that's the direction we're going towards. And I have a lot more slides I'm not going to go through. This is actually a collaboration using the same transformer model on predicting viscoplastic flow in a channel for different Bingham numbers. We wanted to really see, can we break the model? And you absolutely can, right? So for example, if the model hasn't seen enough physics or the magnitude of velocities that are observed in the real flow, it will never be able to predict it, right? So you have to expose your model to diversity of flows and physics. That's always a must, okay? I can go into more details of that, but I don't have time. And now what we're working on is really pre-training these models so it becomes more and more efficient. But hopefully I've shown you Rheoinformatics, again, this made-up word, as this platform that I'm thinking about in terms of data-driven models that can help predict rheology from formulation and synthesis. We've done that with the shampoo models. Model detection, characterization, and constructions. You can actually do accurate rheology predictions, complex flow modeling, and all of that under this umbrella of data-driven techniques in rheology. So that's really the goal, the long-range goal we have. And I hope to have shown you little snippets of here and there the efforts. It's ongoing. So with that, let me thank my group. These are actually the people who did the work. I take the credit for it. So I'll just stop here and try to answer any questions.
Very much. Questions?
Thank you for the talk. My question was related to this multi-fidelity modeling idea, and you talked about the high fidelity being an experiment, and then simulations of something very roughly fit. My question is, what if your low fidelity measurement is an entirely different experiment? Is this something that you have thought about? So for context, I'm thinking of when we want to run something on an extruder or membrane spinning pilot, this takes all day. You can do like 1, maybe 2 a week. And if something goes wrong, that whole day is done. You try again tomorrow, maybe it'll be better. But I can shove stuff in a rheometer a lot quicker. Are there ways that you've thought about sort of combining those
Interesting. I'm just gonna think out loud because we haven't done it before. The one I showed you requires that your input and output parameters be the same, right? So for example, you're measuring a stress, then you have to measure a stress in the other experiment too, right? But if that's not the case, if you're mixing two completely different set of measurements, what I would say will probably work is an idea people call in image processing as CLIP, which is giving the analogy of cats and dogs, right? People love that for neural networks. Imagine basically training a neural network on images of cats and dogs, and on the side you are also training a neural net on sounds of cats and dogs, and you're clipping the residuals of the two, saying this cat has, by the way, this sound, right? And by doing that, you need way less measurements. So sounds to me like that's what you're describing.
Thank you.
First.
Very nice work, Safa. I've got questions about the last two bits. So thinking about the transformer model. So in general, transformer models are not Markovian. You're using past data to make future predictions, which you have to do obviously in language.
Sure.
But I want to solve an initial value problem. I want, stress at equilibrium at t equals 0, and I want the time evolution operator from there. The approaches, the neural operator and transformer approaches, are you able to do that with those approaches?
The flow simulations are completely non-Markovian. You need past data.
Okay.
The other ones, when you're basically using the same neural operators to train the model, you can actually do initial value problems with. But
Okay.
these are 1D problems we did very simple.
But still, in principle, there you can do.
Hopefully,
Okay.
we haven't really done it, right?
Thanks.
Any more questions? Anyone around the corner? I can't see. Okay, in which case, well, thank you again.
Thank you.